And we're going to talk today, moving forward with our look at two-dimensional motion, we're going to talk about what I call a symmetrical projectile, or really a projectile whose flight is symmetrical. And so what I need to access is a certain device that I don't seem to have right near me. So we're going to look at something that, has a flight like that. It's shot at an angle. Boom! And here are snapshots in time at equal intervals of time, if my physics is right. And I think it is. This shows the position of the object at equal intervals. And I believe you have the same diagram in your notes. So this vector here represents this object's initial velocity. You can see that, well, if that's v naught, we say that it's shot at some launch angle that we'll call theta. All right, and right off the bat, what I hope, I'm going to just move this a little bit, what I hope we can identify, you should be able to identify, is the fact that this thing has components of its initial velocity in each direction. Okay, we call this Vx, we call this V initial in the y direction. And the length of those vectors is not arbitrary. Notice the x component goes as far to the side as the vector does. The y component goes as far vertically as the vector does. So it ought to be a skill that you are comfortable with, drawing those components at the right size, or an appropriate size. All right, so what can we say based on our knowledge to this point about projectile motion? Well, one thing we can say that we know is that, well, we should be able to talk about the horizontal components of velocity. All right, what do you know about the horizontal component of a projectile's velocity? Well, what you know is that those components are always the same, or of equal magnitude, or constant, maybe. Yeah, horizontal velocity is constant. Now, I chose to draw this carefully. You might choose to do the same thing. If you notice, I put the end of every vector right at the beginning of the object's position. Or don't draw those dotted lines. But notice, how long do I make these vectors? Well, make them a good, accurate representation of how fast this thing's going. Okay? And notice they're all the same length. You should definitely draw your horizontal components all the same length because, well, horizontal velocity is constant. Okay? Now, the vertical components of velocity, well, this is something that we looked at a couple of weeks ago, but they demonstrate the same stuff we know from symmetry of motion. And so right off the bat, the first thing I can find is, well, I can find that component of the object's final velocity, right? So here's a same Vx, and here's a V final in the y direction. All right? Now, something interesting to notice, maybe going back a little bit over here, is that why doesn't this vector, why doesn't the velocity vector just go like that? Everyone wants to just connect the dots. Well, remember, these vectors are velocity vectors. They're not displacement vectors. If we wanted to say from this instant to this instant, what's the object's change in position? Well, yes, draw that vector by all means. But we are not talking about the object's change in position. We're talking about how fast it's going and in what direction at any instant. All right? And so this says that at the very first instant in time, this object has a velocity that can be represented like that, and in that direction. So why doesn't the object end up here? Well, it's because the projectile doesn't move in a straight line. You know that, right? Its vertical velocity immediately starts changing, immediately starts getting smaller. And so we go from an initial vertical velocity here to a next vertical velocity that's smaller. All right? And so vertically, while initially it started going, in this direction, its vertical velocity slows down, so it doesn't end up going as high as it would have if it went in a straight line, right? Because its path starts to curve. Its vertical velocity starts getting smaller, right? And then over here on the right, again, we know that this vector and this vector have to have the same size. So says symmetry of motion, right? At equal heights, an object's vertical velocity, vertical speed, is identical. The velocities are in opposite directions, but we say, remember, those velocities are equal and opposite. Well, and so on, right? The velocity gets a little smaller vertically as it goes up. It gets a little smaller vertically again until at the top, we know that the vertical velocity is instantaneously 0. And then the velocities turn around and increase at the same rate that they, the speeds increase on the way down at the same rate that they decreased on the way up, the vertical speeds. All right? And anywhere the entire time here, the vertical acceleration, the only acceleration, is g. All right? We can look at we can look at the total velocity, the actual speed, or really the actual velocity of the object at any instant by, the total velocity is always the resultant of vectors vx and vy. All right, so at that instant, at any instant, you can just draw tip to tail. And what I've seen in a few cases already is, people being a little sloppy and saying, okay, here's an x component, here's a y component, all right, there's the result. Well, that is not the resultant of those two vectors. So you ought to be careful and make sure that when you're drawing a resultant that you're actually thinking about tip to tail addition. All right, moving this vector, at least in your imagination, up to here so that it's tip to tail right there. And then the resultant goes from tail of first to tip of last. So just make sure you're careful about if and when I ask you to draw these resultant vectors, if and when I do, and I will, make sure you're drawing those resultant vectors appropriately. Okay? So here's what we can see. What can we see from this? Well, we can see that two things constantly change as this object moves. One of them is the speed that the object moves at. Right? The magnitude of this resultant vector, this resultant vector, this resultant vector, the magnitudes of those vectors are the speed of the object. And those vectors keep getting shorter and shorter on the way up. Right? Then they keep getting longer and longer on the way down. So speed constantly changes. And what else constantly changes? Well, direction constantly changes. Right? In the first instant, it was moving in this direction. Later on, it's now moving in this direction. Direction has changed. Right? So that's one thing. Velocity, the total velocity is always the resultant of x and y. And the other thing is this. The other thing about the total velocity is, at any instant, it's tangent to the actual curve or trajectory. So what you ought to be able to, crap, I got it wrong at the end. But if you're careful, you can draw a real mathematical parabola if you try to keep a curve that's tangent, try to keep a curve that has tangents like those instantaneous velocities in any instant. So I'll add this. Total velocity is always tangent to the trajectory. Hopefully you've been pausing anywhere you need to. And by you, I mean the person who's running the show up front. Okay? So, again, not any real new physics. Now, please notice that from here on over, this is the one we've done already, right? We've done the one that starts with an initial horizontal velocity and then ends up, later in time traveling some horizontal having some horizontal displacement, falling a certain distance of vertical displacement, and we've talked about how to find or how to relate things like how fast it's going horizontally to, how far it's fallen and how far it goes, horizontally, right? So we've done that half. Now the next thing is just look at the whole darn thing, the whole darn trajectory, all right? One thing that's real important to look at is this idea. So if we look at for a given / constant initial velocity, how does launch angle affect range? So we have, a launcher like our little spring-loaded one that I shot off the top of that ladder the other day. That thing shoots at 5.78 meters per second if you have an 8.3 gram projectile. I just happen to know that. It shoots at that speed no matter what angle you shoot it at. And the question is, how do I make it go far or not far? Again, this is assuming this is for a symmetrical flight. All right. So if we shoot a projectile at a relatively low angle like this, or a relatively steep angle like that, these two things won't end up traveling very far. And important here, before first hitting the ground. Right? This one might go boom, bum, 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 bouncing and rolling, but we're not talking about bouncing and rolling, right? We're talking about when it is a projectile, when gravity is the only force acting on it, so until it first hits the ground. All right? Well, so two things shot either at a small angle or a big angle won't travel very far. They won't have a big delta x, or what we call range. And why not? Well, we can tell why not if we look at the components of this object's initial velocity, or if we look at the components of this object's initial velocity. All right? Yeah. So the question is, what is it about this first case that makes it not go very far? Well, remember, delta x is Vx times t. All right? Well, check it out. This one, here's Vx. That's a big Vx. So that says that, it really could go far if it goes fast horizontally. However, we talked a couple days ago about what is it that controls time in the air. And time in the air is controlled by vertical stuff. All right? So this says if there's a small initial vertical velocity, you get a small time in the air. So it doesn't really matter if you travel fast horizontally. If you're not in the air for a long time, then you're not going to travel very far before you hit the ground. Make sense? Now this one is the opposite, right? This one has, wow, that has a big initial vertical velocity, so that's a big time in the air. However, the whole time it's in the air, it's got this really small Vx. So I don't care how long you're in the air for, if you don't travel fast horizontally while you're in the air, you're not going to go very far. Okay? This one will go really high. That's nice if you want to shoot things really high up in the air. And even higher still if you made this angle even bigger. And even, you know, the highest you could possibly ever make it is if you shoot the thing straight up at a launch angle of 90 degrees. Hopefully, you want to shoot something as high as you can, shoot it straight up. All right, but what we're talking about here is not how high we go, but how far we go horizontally. And this one will travel far horizontally. Uh-oh. And why is that? Well, you know, it doesn't have the biggest, let me move this. It doesn't have the biggest delta x. Sorry, it doesn't have the biggest Vx ever, right? Delta x is Vxt. The Vx isn't huge, but it's pretty big, right? So that's a good size. I'll say good sized horizontal velocity. And it also has a, you know, a pretty good sized initial vertical velocity and therefore time in the air. So both of those things are, you know, pretty big, and you multiply things that are pretty big together and you end up with a big delta x. Any guesses as to what this angle is for the maximum possible range at any given constant initial velocity? I guess 45 degrees. All right. Oh, yeah, right. Now, as it works out, I could get two objects shot from the same launcher to land at the same place, shooting them at two different angles. I'm going to transition over here real quick. And what I mean by that is the following. I could say, give me a little shape action. So let me do this. We take, come on, what are you doing? All right. We take this projectile, boop, and we got to pretty it up a little bit. Let's make it purple. No line at all. Where's no line? Come on, all right, fine, purple. Yeah, we take this projectile and we shoot it at an angle. Hey, at an angle like that. Okay. Now, this thing will cover some. It'll cover some distance, right? You know, it might have a trajectory that looks like this. It goes, and it lands here, right? I shouldn't have picked purple. I can't reproduce purple, right? So it has this delta x. All right. Well, I could use the same initial velocity, but a different launch angle, and get it to land at the same place. And how that works is I could do something like this, and now this trajectory would certainly look different. It would go boom, and land at the same, let's stretch this out a little bit, there you go. Sure, the same delta x. Now the trajectory, like I said, the path this thing takes in the air is very different. It doesn't go as high, right? This one has a big time in the air. This has one This one has a small time in the air. This one has a relatively slow Vx. This one has a big Vx, but we can get them to land at the same place. Classic snowball fight trick, right? Here's one guy, here's the other guy, and you get two snowballs, and you go, and you throw one up in the air, then you smash them one, and you get the same, you hit the guy with the snowball by making him look at the one up in the air, right? You throw one at whatever speed you can throw, it goes way up in the air, and maybe it's going to sort of come close to hitting him. You throw another one at the same speed, but at a different angle, and you can hit the guy. Okay, and the question is, what's the trick? I don't know where you're supposed to write all this, but what's the trick about these launch angles? What's special about this angle as opposed or as compared to that angle? Again, I'm sorry, I know you don't have this slide, but you just got to get this down somewhere. Well, what's special about those angles, you might be able to imagine that, well, here's our 45, right? If we were to shoot like, let's say we shot one not at 45, but at 35. Remember, here's 45. We shoot one at 35, and it has a certain trajectory and lands over here. So the question is, do you have an intuition as to what other angle you could shoot this thing at and get it to land at the same place? Think for a minute. Discuss. Okay, so if we shot this thing not at 35, but at 55, again, same launch speed. Well, this one does this, woo, but still lands there. All right, if you go 10 degrees less than 45 and 10 degrees more than 45, you're going to get the same range. All right, so one way to express the answer to that question is to say, well, angles equally far from 45 degrees, right? 10 degrees less, 10 degrees more. The other way to say it is this. What's special about 35 and 55? Or what if we went 15 degrees away and got to 30 and 60? What's special about those? What if we went 35 degrees away and went to 10 and 80? Well, all those angles add up to 90. So the other way to express this, is it complementary or complementary? I don't know. That's a big one. Complementary angles will yield the same range, delta x, for a given initial velocity. And again, assuming a symmetrical flight. Symmetrical means it lands at the same height it was launched from. The path is symmetrical. All right, so that's good little trivia. Good little trivia. All right, the other thing is this. Let me go back here. There is a proof. There is an expression you can write. Now, I've told you that the only expression we'll ever use for delta x is that one. Okay? But you can prove by expanding what Vx is equal to and by expanding how you calculate the time in the air for a symmetrical projectile, you can come up with an expression that proves that 45 degrees has to yield the largest value of delta x. And when I say you can, I mean you should. That's a challenge problem if you're one to accept challenges. prove this. Prove that 45 yields the greatest range. Again, expand this stuff algebraically. How do you calculate Vx? How do you calculate the time in the air for a symmetrical projectile? This will come out of it. You might need yourself a little trig identity. Ooh, remember your days in trig. Okay? Okay, let's talk about the things you'll have to find. Why does that say Vi and Vi? Well, it should say V naught and V naught Y. All right, 3 things you'll ever have to find for one of these projectiles. All right, one of them is, well, delta X. Oh, well, range, we'll call that. That's the last one. It's the hardest one. But it's the one we've talked about so far. We'll leave this depends on thing for a minute. Now, the other things you could be asked to find, what do you think? What do you see? I mean, literally, well, here's what we call delta Y max. So that's max height. The other one that we've talked about a couple times is, maybe we'll call it hang time, or time in the air. You don't really need the air part there. And what am I trying to get at? Well, what does maximum height stuff depend on? Well, how high one of these things goes depends only on the initial vertical velocity. Hopefully that makes sense. I mean, we could say it depends on the launch angle, but the initial vertical velocity depends on the launch angle. So best to say it this way. Depends on vertical stuff. Time in the air, we keep saying, well, yeah, we've said it a couple times now, same, only on V naught Y, only on vertical stuff. How far you go as a range, this is the tricky one. Depends on both X and Y stuff. Right? Remember, if we say delta X is VXT, well, there's your horizontal stuff, but time in the air is vertical stuff. That's why the delta X is the hardest problem. It typically involves doing some analysis of the horizontal stuff and of the vertical stuff. Whereas with these other ones, you only have to worry about vertical stuff. Let's look at a couple of examples. Oh, remember, this is what we call, here's our vector delta X. We can't draw time in the air, right? It's not a vector. So, I made you some assumptions here, arbitrarily. Let's say this thing is shot at an initial velocity of 23.5 meters per second, and a launch angle of 37.5 degrees, and we want to figure out how long it spends in the air. Well, you better get used to that if you're not already. Okay, what do we know? Well, V initial, V naught, is not in the X or the Y direction. However, these components, the initial Y and Vx, well, they are. So Vx, V naught Y, we need to be able to express the magnitude of those components in terms of this and this. V naught, Vx, V naught Y, drawn a little bit differently, all right? Here's theta. Well, this is going back to our vector component days. If that's completely foreign to you, then you need to go back and look over vector component stuff, all right? Or just say, wait, well, where does that come from? Well, cosine of theta is adjacent over hypotenuse, and therefore, yep, that's true. Sine of theta is, I wouldn't be writing all this stuff down, by the way. Sine is opposite over hypotenuse, and therefore, yep, that's true. So what you really need to do, be able to do, is not recreate the wheel every time and say, what do I do? You need to just automatically do that. Okay, you need to be able to get there as fast as humanly possible. All right, hopefully that shouldn't be a major sticking point as to how these problems are solved, just doing some fairly basic trigonometry. Okay, so that's going to be here, V excuse me, naught cosine theta, V naught sine theta. What else do we know? Well, the big thing we know is that the final vertical velocity is the same as the initial vertical velocity, but in the opposite direction. Right? This is from our symmetry of motion stuff. Just because this thing's also moving horizontally doesn't mean that the vertical stuff is different than just a regular free fall situation. It's the same thing. All right, we also know that A is G. Yeah, I'll just leave it as that. What else do we know? Well, nothing. Well, you could say, here's one thing you could say if you want. You can say delta y is 0. Now, if we're talking about the total time the thing's in the air, that means from here to here. Yes, it goes up in the air and comes back down. But delta y, change in position, is just compare the initial height to the final height. And they are the same thing. So you can use the fact that delta y is 0. Now, we actually have too much stuff to put into one equation, but I'll show you 2 ways to do it. Now, remember, if this is flight duration, we don't even care about this stuff. This stuff is not of any importance to us right now. Okay? Here's method 1. Method 1 is use, let's see, assume that we've calculated this. I'll assume that you will calculate it. So therefore, we know both of these, and we know this. So that means we can use the following. Whoops, not that following. We can use final vertical velocity, geez Louise, is initial vertical velocity plus gt. I'll write that like this. Well, Vy, we just said, is negative V naught y. And this is negative 2 V naught y equals gt. Or t is negative 2 V naught y over g. Or negative 2, well, V naught y is V naught sine theta over g. There's an expression for how long a projectile spends in the air, assuming you know its initial velocity and the angle it's shot at. Okay? Method 2 is to use this. Delta y is V naught yt plus 1/2 gt squared. V naught y is 0. So we get negative V naught y times t equals 1/2 gt squared. Well, divide both sides by a factor of t. And then solve for t. We get t is negative 2 V naught y divided by g. Oh yeah, same thing. So I don't care which one of those ways you use, but this is the expression for time spent in the air. I trust you can calculate. I get, let's see, 2 times 37, no, 2 times 23.5 times the sine of 37.5 divided by 9.8. 2.92. Now, you didn't hear me say anything about negative here. Why is this negative here? And well, that's because this is the initial vertical velocity, right? That's upward. This is g downward. So those have to have opposite signs, and then the negative makes t come out positive. Okay? Okay? Come on. Okay. Where are we? Whoa. What happened? Yeah, okay. So next question, dy, this should say delta y max. We want to know how high you go. And remember, this only, force of habit, which I hope becomes your habit, always start with x stuff and y stuff, right? I'm going to rewrite what we know. All right. Now, at maximum height, what do we know? Well, we know that our final velocity is going to be 0 for that one instant at the top. Okay? This is upward, A is g downward, and we want delta y. All right, well, there's one equation that has those four things in it, and it looks like this. Vy squared is v naught y squared plus 2g delta y. That goes. So says algebra. Agreed? Right? That's v naught y. Here's v naught y. Don't forget to square it. Divide by 2g. Okay? So that would be, now the negative, again, is because, well, v naught y is upward, g is downward, and that makes this, or the negative makes delta y come out upward. All right? Let's say that we're using that sign convention. All right, we'll get let's see, v naught is 23.5 times the sine of 37.5 squared divided by, well, let's just call it 20. So delta y, I get 10.2 meters. All right, I'll do the substitution here. Negative 23.5 sine 37.5 squared divided by negative, right? Two negative signs make our delta y positive, meaning upward. Yes? Yes. Now, arrange delta x. This is the hard one, but luckily we've done most of the legwork already, right? Remembering that we're going to have to use that to find delta x. This says we do need x stuff. Vx is v naught cosine theta. All right, t, remember, that depends on y stuff. V naught y is v naught sine theta. Remember, v final y is negative v naught y, right? A is g. Let's see, and this is upward, and that's downward, and that's downward. And we want to find t, and I'll refer you back to what we did 2 slides ago for how we found time in the air. I'll just show you. I didn't give you an answer here. Oh yeah, I did. 2.92 seconds. Right? So I assume that, well, you would, I would hope, do the same exact thing to find time in the air. Right? Well, which really boils down to this. Negative 2 v naught sine theta over g. So let's say that, you know, we remember we get 2.92 seconds. So then our delta x is going to be v naught cosine theta times t. 23.5 cosine 37.5 times 2.92 seconds. How far does this thing go? 23.5 cosine 37.5 times 2.92 equals 54. Okay? What do you think? Well, you know what? Well, even before this video, I would argue that you knew everything there was to know about how to solve symmetrical projectile problems. We just formalized a few things. You know, perhaps the most important parts are the simple things like this. You got to make sure you're using components correctly. All right. This, right, is an application of stuff that we focused on in one-dimensional motion, but that certainly applies here. All right. So there's it's again not a ton of new stuff, but just applying the same stuff to more complicated situations. All right. You should now be able to work through the next, hang on, wait for it. Yeah, we'll be able to work through, I would say for the next time I see you in lab, you should have, let me switch and make sure I write this down. This is really for B-Day folk. A-Day folk, you're a whole different animal. But for B-Day folk, for next lab, we want to see 8, 9, 10. Yeah, sure. Let's go with those. Okay? Okay. That's going to be it, folks. This is a long one, I understand. Thanks for your patience. Like I said, I won't be missing much soon. All right? So, see you, folks.